Welcome dear students. We are going to see the heterocyclic compounds part second. In this we are going to see about the 6-member heterocycle and the condensed heterocycle. The 6-member heterocycle example is the pyridine. Pyridine is the most important heterocycles. It occurs along with the pyrrole in the bone oil. The next point is the synthesis of the pyridine from acetylene. By passing the mixture of acetylene and hydrogen cyanide through a red hot tube, we will get here the pyridine. These are the two molecules of acetylene and this one is the hydrogen cyanide HCN. The CH-CH bond is formed after moving this bond here. This CH-CH single bond is formed after moving the single bond in between this gap. The CH and N bond is formed after moving the bond here. Means in red hot tube we will get the pyridine. The second reaction is synthesis from beta-picoline. This involves the oxidation of the beta-picoline with potassium dichromate and sulfuric acid to give the nicotinic acid. The nicotinic acid on decarboxylation with calcium oxide gives the pyridine. This is the beta-picoline at 3 number position. CH3 group is present, which is oxidized and converted into the COH group with the help of potassium dichromate in the acidic condition. This nicotinic acid on decarboxylation, that is removal of CO2 group, it will give us the pyridine. The third method of synthesis is from pentamethylene diamine hydrochloride. On heating, in the presence of a base, forms the pyridine, which on dehydrogenation forms the pyridine. This is the pentamethylene diamine, means 5 methylene group, 5 CH3 group means pentamethylene. Diamine means 2 NH2 group and hydrochloride means 2 molecules of HCl. Dihydrochloride means 2 molecules of HCl. And upon heating, we will get here the pyridine, which on dehydrogenation with concentrated H2SO4, we will get here the pyridine. The physical properties of the pyridine. Pyridine is the colorless liquid. Its boiling point is 115 degrees centigrade temperature. It has a very characteristic pungent and disgusting, means we cannot smell easily. It's very disgusting odor. The third physical property is the pyridine is miscible with the water and most organic solvent. It is very hygroscopic. Hygroscopic means it absorbs the moisture. So pyridine is miscible with organic as well as inorganic solvents. The fourth physical property is almost all classes of the organic compounds are soluble in the pyridine. The fifth point is the pyridine forms azeotrophs with the water, which boils at 92 to 93 degree, means its boiling point is lowered in azeotropic mixture when it is mixed with the water. The chemical properties. The pyridine shows the both types of chemical property, that is electrophilic substitution reactions and the nucleophilic substitution reactions. First we will see about the electrophilic substitution reactions. In this, first one is the nitration. The pyridine undergoes the nitration with potassium nitrate KNO3 in the presence of sulfuric acid at 300 degree centigrade temperature to give the 3-nitropyridine. This is the potassium nitrate. After dissociation, it will form the K plus and NO3 minus. This NO3 minus attacks on the pyridine ring at 3 number position and we will get here the 3-nitropyridine. The sulfonation. Pyridine undergoes the sulfonation with fuming sulfuric acid in the presence of mercury sulfate HgSO4 at 230 degree centigrade temperature to give the pyridine 3-sulfonic acid. This is the sulfuric acid and this catalyst is mercury sulfate. Upon sulfonation, we will get here the 3-pyridine sulfonic acid. The third electrophilic substitution reaction is the bromination. Pyridine may be brominated by passing the vapors of pyridine and bromine over the charcoal catalyst at 300 degrees centigrade to give the 3-bromopyridine and 3,5-dibromopyridine. This is the bromine molecule. It gets dissociated when dissolved in the charcoal. It will form the Br plus and Br minus. This Br plus attacks on the 3 number position of the pyridine and other side product is the 3,5-dibromopyridine. Nucleophilic substitution reaction. Pyridine is highly reactive towards the nucleophilic substitution and it is mainly occurs at 2 number position The general mechanism of electrophilic substitution reaction of the pyridine is as follows. This carbon, here is CH bond is present and here is nitrogen. The nitrogen is more electronegative than the carbon, that's why the pi bonded electron attracted towards this nitrogen atom, means there is a formation of the positive charge at 2 number position and negative charge at the on the nitrogen atom. This negative charge of nitrogen atom will break the neighboring double bond, and this will create here the positive charge. This positive charge and this negative charge will form here the one bond, double bond, and here is the remaining negative charge. This negative charge will again break this next coming bond, and here is leaving only the positive charge. This positive charge and this negative charge will forms here again double bond. Here is a negative charge. This negative charge liberates the H minus, means hydride ion is removed. This arrow you can consider in a reverse manner, means hydrogen in this case not going in H plus form, it is going in the H minus, means hydride form, means here leaving the positive charge. This positive charge and this negative charge combines together to form the double bond. This is the general nucleophilic substitution reactions. And the nucleophile may be the NH2 minus, OH minus, C4H9 minus. The first reaction of the nucleophilic substitution reaction is the amination reaction. The reaction with the soda amide with pyridine is also called as Chichibabin reactions. In this, pyridine reacts with the soda amide, means NaNH2, in liquid ammonia as a solvent at 100 degrees centigrade to form the 2-amino pyridine. This is the pyridine. This Na plus and NH2 minus is formed when dissolved in the liquid ammonia. This NH2 minus will attack on this 2 number position where already positive charge is created, and we will get here the 2-amino pyridine. The second nucleophilic substitution reaction is reaction with the KOH. Pyridine reacts with the potassium hydroxide at 300 degrees centigrade to yield the equilibrium mixture of the 2-hydroxypyridine and 2-pyridone. This reaction is carried out in the presence of the oxygen or in presence of the air. This is the K plus and OH minus is formed. This OH minus ion as a nucleophile attacks on the 2 number position of the pyridine ring, and here is formation of the 2-hydroxypyridine. It is in the enol form. En means double bond, OL means OH. This enol form is not that much stable. It is converted into the keto form that we will call as 2-pyridone. The third nucleophilic substitution reaction is the reaction with N-butyl lithium. Pyridine reacts with the N-butyl lithium at 100 degrees centigrade to give the 2-N-butyl pyridine. This is the N-butyl lithium. Lithium is electropositive than carbon. That's why the lithium atom liberates the electron that is accepted by this CH2 carbon atom. This CH2 makes here negative charge after accepting the electron from the lithium atom. Lithium atom becomes positive charge. This CH2 negative charge acts as a nucleophile. This complete is butyl anion will attacks on the 2 number position of the pyridine, and here is formation of the N-butyl pyridine. This is the CH2, 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 CH3. The fourth reaction is the reduction reaction, means addition of hydrogen atom on the pyridine ring. The pyrrole undergoes the reduction with the lithium aluminum hydride, that is LiLH4, or hydrogen in the presence of a nickel catalyst to form the pi-pyridine. This is the catalytic reduction. In this, the pyridine on reaction with 3 molecules of hydrogen in presence of nickel as a catalyst, here we will get the pi-pyridine. The other method is the pyridine on reduction with lithium aluminum hydride in aqueous solvent, that is alcohol or ethanol, we will get here the pi-pyridine. Oxidation means addition of oxygen atom on the pyridine ring. Like benzene, pyridine is quite stable towards the mild oxidizing agent. That's why we have to make its oxidation by using the peracetic acid. Means it contains the extra oxygen atom as compared to acetic acid. Means this is the peracetic acid. This peracetic acid on oxidation on pyridine, it will form the pyridine N oxide. Pyridine N oxides electrophilic and nucleophilic substitution reaction is opposite to that of the pyridine. Means it gives opposite reaction to that of the pyridine. The basic character of the pyridine. The base is that compound or molecule which donates the lone pair or accepts the hydrogen atom. Here is the pyridine. In outside there are one lone pair of electron of the nitrogen atom. This HCl is acid. This H plus will accepted by this pyridine nitrogen atom, means it accepts the proton, means it is a base, and its pK value is 5.2, and there is formation of the salt. That's why it is pyridine is also called as a base. The condensed heterocycle. In this section we are going to see only the synthesis of the indole and the quinoline. The first one is the indole. Indole consists of a benzene ring fused with the alpha beta position of the pyrrole ring, means benzene ring is fused with this pyrrole ring, that's why it is called as benzopyrrole. The synthesis of indole from Fischer-indole synthesis. In this method, phenylhydrazine, this is the phenylhydrazine, is treated with aldehyde or the ketone, this is the aldehyde, in the presence of a zinc chloride to form the corresponding phenylhydrazone, which on further 3,3 shift or Claisen rearrangement we will get the indole as the main product. This is the phenylhydrazine and this is the acetaldehyde. First one is the dehydration reaction. This H2 and this O combines, there is formation of the H2O molecule. This nitrogen atom will joins with this double bond. Here we can see here the double bond. The remaining part is as it is. Then 3,3 shift. This is the one carbon atom. First consider this as the first carbon, this is second carbon, and this one nitrogen atom is the third. This CH2 is first carbon, this is the second carbon, and nitrogen atom is considered as the third. In this we have to break this 3,3 bond, means the bond between the 3,3 gets broken, the bond between this 1 and 1 gets joined, and there is formation of double bond between this 2,3, means there is a breaking of bond between 3,3, joining of the bonds between the 1,1 and obtaining the double bonds between the 2,3. Here is the double bond is present, and here is the double bond is present in the next coming reaction. Here we can see this structure. After 3,3 shift, this proton gets migrated as 1,3 shift, 1, 2, 3 shift. This is 1,3 shift. After 1,3 shift, here we can see that there is a formation of the NH2 bond, and there is cyclization or aromatization. This NH2 group attacks on the CH positive charge, that is carbocation, after breaking of this bond. Here we can see this structure. This proton and this NH2 minus will get liberated and formation of the NH3, and we will get here our desired product as indole. The second synthesis of indole is Bischler's indole synthesis. When the aniline reacts with the alpha bromoacetaldehyde in a reflux in presence of HCl, we will get the indole. This is the aniline and this is the alpha bromoacetaldehyde. This Br and this H will get liberated as HBr, and there is a formation of the bond between the NH and this CH2, and there is again cyclization with this proton and this OH group. After enol bond formation, we will get here the indole as the product. The second condensed heterocycle is the quinoline. Quinoline consists of the benzene ring fused with the alpha beta position of the pyridine ring, means benzene fused with the pyridine ring. It derives its name from the fact that it was first obtained by heating the famous antimalarial alkaloid quinine with the alkali quinoline. Occurs in the coal tar, bone oil, and in the augusta bark. This is the quinoline. This benzene ring is fused with this pyridine ring. That's why its IUPAC name is benzopyridine. The common name is quinoline. Synthesis of quinoline from syrup quinoline synthesis. In this reaction, a mixture of aniline and glycerol. The mixture of aniline and glycerol is heated in the presence of sulfuric acid and nitrobenzene. The reaction is exothermic and tends to become very violent. The ferrous sulfate or boric acid is generated, added to make the reaction violent. This is the aniline, and this is the total overall reaction of this fish syrup quinoline synthesis. This is the aniline, and here is the glycerol, here is concentrated H2SO4, here is the nitrobenzene, and we will get here the benzopyridine or the quinoline. The first reaction happens in between the glycerol and concentrated H2SO4, means dehydration reaction. After removal of the water molecule, we will get here the acrolein, means alpha beta unsaturated aldehyde. This alpha beta unsaturated aldehyde will get added like Michael addition. This lone pair of electron will attach on this CH2 plus charge, which is formed after the breaking of this CH2 CH bond. Means this one bond is broken, CH carries the negative charge and CH2 carries the positive charge. The lone pair contains one positive charge and one negative charge. This negative charge combines with this CH2 positive charge, means one negative and one positive charge creates the one single bond or form the one single bond. And this CH negative charge and here positive charge, means here is formation of the double bond, and here is O negative charge. This O negative charge and this removal of after H plus from NH2, we will get the OH. In the second step, we will see here that formation of the H2 molecule from hydrogen atom from the this benzene side and OH from this side. There is formation of the H2O molecule and there is a ring closure reaction or cyclization reaction. It is also happens in the presence of the concentrated H2SO4. Here we can see that this structure is 1,2-dihydroquinoline is formed. Means again we have to remove one hydrogen molecule, H2 molecule. For that we have to require this nitrobenzene, which is oxidizing agent. One hydrogen from here, one hydrogen from here gets removed with the help of nitrobenzene, and here we will get finally the quinoline as our desired product. The last synthesis of the quinoline is a Friedlander synthesis. This involves the condensation of orthoamino-benzaldehyde with acetaldehyde in the presence of alkali. This is the orthoamino-benzaldehyde. At 1,2 position, amino and aldehyde group is present. That's why it is called orthoamino-benzaldehyde. And here is acetaldehyde. This NH2, this hydrogen and this oxygen gets combined and formation of the H2 molecule. This H2 from CH3 and oxygen from this aldehyde group, formation of second H2 molecule, and here we will get the quinoline as our desired product. The remaining part we will see in the third part of the heterocyclic compounds.